or a pull. That's the basic rule. That's a force, baby.
Welcome to Phantastic Physics. Today we're going to talk about forces. What is a force? What can a force do? And how do forces affect the motion of objects in our universe? Well, let's start with what a force is. It's actually very basic. A force is any push or pull. So if I take this textbook and push it across the table, I'm applying a force to it. Or if I were to tie some rope around it and pull it towards me, that's also a force. Okay, so we know what a force is. It's pretty basic. But what do forces do? Well, forces cause objects to change their motion. So whatever an object is doing before a force, if you apply a force to it, its motion is going to be different. Something's going to change. And more specifically, forces cause objects to change their velocity. So when I say a force causes an object's velocity to change, we have to first understand what I mean by the word velocity. So a velocity is a speed plus a direction. So if I say I'm moving at 25 meters per second, that's my speed. And if I say I'm moving in the forward direction, that's the direction part. So a speed plus a direction is a velocity. If I apply a force to some object, I cause that object's velocity to change, which means either its speed changes or its direction changes. A force causes a change in speed or a change in direction. Well, what are the two ways that we can change speed? Well, you could speed up or you could slow down. And that means there's really three outcomes. When a force is applied to any object in the universe, either that object will speed up, it will slow down, or it will change direction. Or it could do more than one of these things, right? It could speed up and change direction or slow down and change direction. But it has to do at least one of these things whenever a force is applied to an object. So that's what forces do. They change the velocity of an object in one of these three ways. If you're driving a car, you could apply a forward force by stepping on the gas pedal. That would be the way to speed up. You could step on the brakes if you wanted to slow down. That applies a reverse force. And if you wanted to change direction, you could turn the steering wheel, which applies a sideways force. Another word to describe change in velocity is acceleration. So in physics, we say that a force will always cause an object to accelerate. Forces cause accelerations. Nothing in this universe would ever accelerate without a force acting upon it. So let's look at some examples. Here is a textbook, and I'm going to go ahead and just put my palm out flat and hold it like this. So first question, is this textbook accelerating? Well, I think it's pretty clear that its velocity is not changing, therefore it can't be accelerating. So does that mean there's no force acting on it? Well, think about it. There has to be some force acting on this book, right? So what force is that? Can you think of at least one force? And most people are pretty quick to say that the Earth's gravitational pull is pulling down on this book. So the force of gravity should be acting on it. And that's right. Well, which way does gravity act? Downward. So there's a downward force of gravity acting on this book. Then why is it not accelerating if there's a force acting on it? Well, that's because there's a second force acting on this book. What is the force that's preventing this book from falling? Because if it was just gravity, it would accelerate downward. Well, that force is the force of my hand pushing back up on the textbook. And in physics, when a surface, like the table, the ground, my hand, really anything, when a surface holds an object up, we call that the normal force, N-O-R-M-A-L. And the reason we call it a normal force is because it is normal or perpendicular 90 degrees from the surface. So if my hand is a horizontal surface, the normal force acts perpendicular to that surface, or normal. So here is a simple diagram of my textbook and the forces that are acting on it while I'm holding it in my hand. Remember, we said there's a force of gravity pulling downward, which we label as F sub G. And then the normal force is F sub N. So these are just subscripts to basically distinguish what kind of force it is, okay? So which of these two forces is stronger? Is it the normal force or the force of gravity? Think about that for a second. Which of these is the stronger force? And some people might be tempted to say that gravity should be stronger because the entire planet is pulling this book down. How could my hand possibly be pushing up with more force than that? But that's incorrect, because if this force of gravity was stronger, if I drew it as a longer arrow, then this stronger force would cause this thing to fall. It would sink right through my hand, which would be weird. So it can't be stronger. Well, could the normal force be stronger? Is that the stronger force, me pushing up on the book? Well, that can't be right either, because then there would be, here, let me draw this as a short arrow here. If the upward force is stronger than the downward force, the overall force would be in the upward direction, which means this book would start accelerating up and rising into the air. And that doesn't make any sense. So if this book is not accelerating, that means the force in the upward direction should be exactly as strong as the force in the downward direction, which means it should be like this, equal forces, so that they cancel out. And that brings us to my next topic, which is something called net force. And net force, which is shown as F sub net, is a way of saying total force or overall force. So the net force on this book has to be equal to 0, because if it's anything but 0, it's going to accelerate. But we know this book was not accelerating. So whenever you have a net force of 0, you have an object that is not going to accelerate. And that means, basically, we can say that the normal force from my hand pushing up on the book minus the force of gravity, so upward force minus downward force, has to come out to be 0. Now, what does this mean? That means our normal force is equal to the force of gravity, as we said before. I'm just bringing this term to the other side. So that means if I were to weigh this book and get its gravitational force, because remember, weight and force of gravity actually mean the same thing. So if this book weighs 10 newtons, what do we know about the normal force of my hand pushing up on it? Well, we know that must also be 10 newtons. So whatever force is pulling down on it is exactly equal to the force pushing up on it. By the way, this was an object at rest, and because there was a net force of 0, it stayed at rest. This is actually Newton's first law of motion. An object in motion will stay in motion unless an outside net force acts on it. An object at rest will stay at rest unless an outside net force acts on it. So the only way this object could move, of course, is if there was a net force not equal to 0. Okay, let's look in the horizontal direction now. So let's say I took this textbook and I placed it on the table and I gave it a push to the right, okay? So in physics, we usually label that kind of force as an applied force. So I'll call that F applied. And that's just a generic term for any external push or pull acting on an object. So imagine I come up and I start pushing this book to the right with an applied force. Can you think of any other forces acting on this book as it sits on the table? Well, yeah, just like when it was in my hand, if it's on a surface, on a table, there has to be some kind of normal force holding it up so that it doesn't sink through the table. And of course, there is a force of gravity because the Earth's always trying to pull down on this book. And as we said before, these two forces have to be equal so that it doesn't start flying or sinking through the desk. Now, is there any other force acting on this textbook as I push it to the right? You probably guessed there should be some friction here, right? So I'm going to label this as F. This is a backwards pointing force because the force of friction is always going to oppose a moving object. So if it's sliding to the right as I push it, friction between the textbook and the desk is a force that's trying to slow it down. It's acting to the left. Now, I purposely drew the applied force greater than the force of friction. So if I were to ignore the up and down stuff, which direction does the net force act on this book? In other words, in which direction is the overall force pointing? You can probably tell that the net force points to the right, and that's the direction that the overall force is pointing because there's more applied force from my hand than there is from the friction that's trying to slow it down, okay? And of course, if the net force points to the right, guess which way this book accelerates? To the right. And that brings us to the most important thing to remember about force and acceleration. Whichever way the net force points is the same direction that an object will accelerate in. Okay, so what about the moment after the textbook leaves my hand? So imagine I'm pushing it and then I let go and the book starts sliding on its own, okay? So after I stop touching it with my hand, is there still an applied force acting on that textbook as it slides on its own? And the answer is no. So this force is now gone. Are these two forces still here? Of course, it's still on a desk, so there has to be a normal force. There's still a planet Earth beneath us, so it has to be pulled down with gravity. But now our diagram looks like this. There's no more applied force. There's just the force of friction as it slides by itself. So when you look at this diagram now, in which way is the net force pointing? Well, it's very clear that the net force, the overall force, is now to the left. And if the net force is pointing to the left, in which direction is this textbook accelerating as it slides to the right? Well, it has to accelerate in the same direction as the net force. So even though it's moving to the right, it's actually accelerating to the left. And that brings us to another important thing to understand about force and acceleration. If you're ever moving in one direction, but you're accelerating in the opposite direction of your motion, what that means is you will always slow down. And that's the reason this textbook slows down and comes to a stop after it leaves my hand, because the net force is now pointing left, which means it accelerates the opposite direction that it's moving, and therefore it slows down and eventually stops. Now that we know the basics of how force and acceleration work, we can do a more complicated problem. So this here is a 747 passenger airplane, and let's say that it's taking off from the runway and it's got all 4 of its engines active, and each engine is producing 250,000 newtons of thrust. So we have 4 forces, 1, 2, 3, 4, and each of those is 250,000 newtons of thrust pushing this plane forward. So we have 4 of them. Quite a bit of force, okay? And we're gonna simplify things a little bit and say that there is some air resistance, which we can label as F air. And even though air resistance increases when the plane gets faster and faster, we're gonna simplify it and just say it's a constant 100,000 newtons of air resistance. And that's a backward force. It's the air particles pushing against this plane, trying to slow it down. And let's also say that the force of friction between the wheels and the ground is also equal to 100,000 newtons. So we have a total of 6 forces. 4 of them are due to the 4 engines producing a thrust that's pushing the jet forward, or the airplane forward. And then we have 2 resisting forces due to friction and air resistance. So if we wanted to calculate the net force here, what do we have? Well, first let's establish that this is our positive direction and to the left will be our negative direction. So we have 4 times 250,000, which is 1 million. So 1,000,000 newtons pushing forward, minus 2 times 100,000. So minus 200,000. So 1 million minus 200,000 gives us a net force of 800,000 newtons. So our net force came out as a positive answer, which means the overall net force is in the forward direction, the positive direction. So what that means is all 6 of these forces could be replaced with a single force that's equal to 800,000 newtons, and that is equivalent to all of this, okay? So now I've gone ahead and replaced all of my forces on my diagram with just the single force here, the net force of 800,000 newtons, because remember, it's equivalent to all the others. And I had to look this number up, so this is a reasonable guess for a 747 that is not completely loaded with passengers and cargo, but fairly loaded. And so we have 400,000 kilograms of mass. This is the mass of this airplane, and this is the net force acting on it. So now we can use Newton's second law of motion. And that tells us that the acceleration of any object is just equal to the net force acting on the object divided by its mass. And so if I take this net force and divide by this mass, I can actually calculate and predict the acceleration of this airplane as it takes off and prepares to lift off into the air. So let's go ahead and do that calculation. Remember, we have 800,000 newtons divided by 400,000 kilograms. And I have some easy numbers here. So this is just going to give us 2. So we get an acceleration of 2 meters per second squared. So what is a meter per second squared? That's the standard unit of acceleration in physics. So what that means is every second that goes by, every second this thing is moving forward, its velocity or its speed will increase by a rate of 2 meters per second each second. So after 1 second, it's going 2 meters per second, then 4, then 6, then 8. So this acceleration tells us the rate at which it's increasing its velocity before it takes off. One other thing to notice is the acceleration came out as a positive number, which means it's accelerating to the right, our positive direction. And remember how I said the acceleration should always be in the same direction as the net force. Because we have a rightward pointing net force, we of course get a rightward pointing acceleration. Okay, so we know the rate at which this airplane is accelerating when it's taking off. Here's one more interesting thing you can do with a problem like this. Let's assume that in order to have a successful takeoff, it needs to reach a final velocity of 70 meters per second. So in other words, by the time it gets to the end of the runway, it needs to be moving this fast to take off. So VF stands for final velocity. This is what we're trying to achieve. So the question we can answer is, how much time is this airplane accelerating for at this rate in order to reach this final velocity? So how much time will it spend accelerating on the runway in order to get to this speed? And that's actually a pretty easy problem to solve. And we're going to use this equation. Remember how I said acceleration is defined as a change in velocity over a period of time. And so this triangle symbol stands for delta from the Greek alphabet. So delta V, or change in velocity divided by time, that's the definition of acceleration. So what is a change in velocity? Well, that's just your final velocity minus your initial velocity. And that's going to be divided by time. So this is an equation that lets you calculate acceleration using your final velocity, your initial velocity, and the time you're accelerating. Well, what do we know in this equation? We already know A. It's accelerating at a rate of 2 meters per second squared. So I can plug in 2 meters per second squared on the left side of the equation for A. What goes on top there? Well, I know the final velocity, right? I need to reach this speed to take off. So that's 70 meters per second. That's going to go there for VF. Well, what's the initial velocity of this airplane? Well, it starts at a speed of 0. It has an initial velocity of 0. So minus 0 meters per second. And then that's divided by time. So we know everything except for the time, and that's what we're going to solve for. On the left side, we have 2. On the right, what's 70 minus 0? That's just 70. And that's divided by time. Now, the next thing we can do is just multiply both sides by t, right? So the t is going to cancel itself on the right side, so it's gone. And on the left, we have 2 times t. So now we have 2t on the left side is equal to 70 on the right. So then what's t? Well, I'm going to divide both sides by 2. The 2's will cancel, and I'm left with t equals 70 over 2. So t is equal to 35 seconds. So that means this airplane will be accelerating at a rate of 2 meters per second squared for a total time of 35 seconds by the time it reaches the end of the runway, and it will leave the runway at a velocity of 70 meters per second. All of this was done just by knowing the forces acting on this object, calculating the net force, which enabled us to calculate the acceleration, which enabled us to calculate the time. Pretty neat.